Okay, today I will talk about radioactive decay. Radioactive decay happens when an unstable atom loses energy. The atom gives out radiation. This process happens by itself and we cannot control it. When an atom decays, it can change into another element or into different form of the same element. This continues until the atom becomes stable. Another important idea is called half-life. Half-life is the time needed for half of the radioactive material to decay.
Now, let's focus on the mathematical model shown here. We start with the differential equation of radioactive decay is dm over dt equals to negative km. This equation tells us that the rate of change of m with respect to time is proportional to the value of m itself. The negative sign shows that the value of m decreases as time increases. To solve this equation, the first step is to separate the variables. We rearrange the equation so that all terms involving m are on one side and all terms involving t are on the other side. This gives us 1 over m dm equals to minus k dt. Next, we integrate both sides of the equation. After integration, we obtain ln m equals to negative kt plus c, where c is the constant of integration. To remove the natural logarithm, we take the exponential of both sides. This results in m equals to e to the power of negative kt plus c. Using the laws of exponent, we can rewrite this expression as m equals to e to the power of c times e to the power of negative kt. Since e to the power of c is constant, we simplify it by replacing it with a single constant c. Therefore, the final solution of the differential equation is m of the t equals to c e to the power of negative kt. This formula allows us to express the value of m as a function of time. Once the constant c and the value of k are known, we can determine the value of m at any specific time.
This is our first problem statement. An animal fossil contains 500 mg of radioactive isotope. After 1 year, 2% of the isotope has decayed. If amount of the isotope decays proportionally to the amount present, calculate the half-life of the isotope. So, we can see the solution.
Let's understand what the question is telling us. We are given a situation where 2% of the substance decays every year. That means every year 2% is lost, so 98% of the substance remain because the decay depends on how much is present. This situation is best modeled using an exponential decay formula. So the general formula for exponential decay is m bracket t equal to ce power of negative kt. M bracket t is the amount of the remaining after time t. C is the initial amount, k is the decay constant, and t is the time in years. Now let's apply the information given in the question. At time t equal to 0, which means m bracket 0 equal to c. This makes sense because at the beginning the amount is just the initial amount. Next, substitute t equal to 1 into the decay formula, which is m bracket 1 equal to ce to the power of negative k bracket 1. But we already know that m bracket 1 equal to 0.98 c, so we equate them to 0.98 c equal to ce to the power of negative k. Next, we take the natural logarithm on both sides, which is ln power of e power of negative k equal to ln power of 0.98, and then we get k equal to negative ln 0.98, and then the value k that we got is 0.0202. And now we have the decay constants. Next, we substitute the value of k back into the formula. So the exponential decay model become m bracket t equal to CE the power of negative 0.0202t. And then this equation asks us to find the half-life, right? So we put them in 1/2c equal to CE to the power of negative 0.0202t. And then we use the logarithm, which is ln power of 1/2 equal to ln to the power of e to the power of negative 0.0202t. And we solve that, and we get the t, which is 34.31, and then we approximately to the 34 yes. So that's the answer for this question.
Now, I will present the second problem statement. A radioactive substance decays at a rate proportional to the amount remaining. This statement means that the rate at which the radioactive substance decays depends on how much of the substance is still present at any given time rather than on its initial amount. 1/3 of the initial amount decays into a new substance after 5 minutes. In other words, after 5 minutes have passed, 1/3 of the original quantity of the substance has already undergone radioactive decay. In addition, it is given that 50 grams of the substance has decayed after 12 minutes. This information provides us with another condition that helps describe the decay process over time. The question then asks us to find the initial amount of the radioactive substance. Therefore, based on the given information, the main objective of this problem is to determine the original quantity of the substance before any decay occurred using the principles of radioactive decay and differential equation, which will be demonstrated in the solution part.
I will explain the solution for that problem step by step. First, we know the general equation of radioactive decay, which is Mt equal to Ce power of negative kT, where C is initial amount, K is decay constant, and T is time in minutes. From the first information given, we know that 1/3 of substance decay after 5 minutes, so that means only 2/3 remaining after 5 minutes. We substitute it into equation and become Ce power of negative 5K equal to 2/3C. We cancel C, we get E power of negative 5K equal to 2/3, and find the value of K by multiply both sides with ln, and then we get the value of K, which is 0.0811. Next, from the second information, we know 50 gram decay after 12 minutes, and the remaining we can put as C minus 50, and then we substitute the value of K that we get earlier, and finally get the initial amount, which is 80.63 grams.
To sum up, this assignment used the idea of exponential decay to stimulate real-world scenario involving radioactive material. The initial amount on the substance will successfully calculate using specific condition, demonstrating how mathematics model it in the explanation of physical phenomena. The study demonstrates the value of differential equation in science and engineering application, and also emphasize their significance in comprehending radioactive decay.